let me talk about how to solve it with CRA utility. And but before, let me take a step back and give a little bit of a big picture. So, and this is going to be a little bit of an introduction to CRA utility as well. Okay. So what is more difficult, economics or physics? So, of course, economics. Of course, it's more difficult because economics is about people, and if you're not studying particles, but you're studying people, that it's crazy difficult. And even if you assume that people are rational, economics is still more difficult than physics. So people are often not rational, but there's a whole behavioral finance and economics on the rise, so we can deal with that as well, maybe. So why economics is more difficult than physics is because in physics we have initial condition and we solve for it. How the planets move around each other or whatever you want to solve. Okay? And in economics we have to solve forward, but we also have to solve backwards. So we have forward equation and we have backward equation. And this wealth distribution evolution equation, this equation is a forward equation. But when we solve for the value functions, it's a backward equation. Okay? And this equation here, this is the money valuation equation. So when we solve for asset prices, we also solve backward because we take into account, the future cash flows, we take into account the future frictions, and we form expectations, and we solve backwards. So we have backwards equations and forward equations. And the value function equations, the Bellman equations, those backward equations. But the value functions, they summarize the future, sufficiently. So once we have those sufficient statistics, then at the given moment of time, we can just focus on the static equations. So they're also static equations. Okay? So there's a forward equation for the wealth distribution. There are backward equations for, we have backward equations for prices of some assets or for value functions. And they haven't talked about the backward equations for the value functions yet. And then we have static equations. And in these models, we have, so let me say, roughly, so maybe you can find out. We have three types of static equations. One of them is asset allocation equation, okay, which is, I think, the hardest equation. Then the second hardest equation, something that I have not introduced yet, is that the equation that determines endogenous risk, okay, the risk generation equation. So in that equation, basically, what happens is that the shocks, they affect the net worth of agents, but so they affect the net worth shares, but the prices, they respond to the changes in the net worth shares, so you get the feedback effect through prices. So basically, you also need an equation like that. And then consumption market clearing is also an important equation, but once everything is set up, this is a very easy. This is the simplest equation. So we have those things. So I want to talk about CRA and I want to talk about computation, but unfortunately I have to start by erasing some things. So because I have to make some room. So let me erase, but as I erase, I'm going to keep some things. And the point I want to make is I want to keep the most important, basically, parts. Okay. So to keep the laws of motion of wealth shares, and I'm going to keep this asset pricing equation. And from this part, what I want to keep is I want to keep, so this is the volatility of marginal utility, and this is minus the volatility of marginal utility. Okay, so basically for CRRA, the risk premium is gamma times sigma c. So this is the volatility of consumption. Okay? Because so why this is the case? Well, because the marginal utility is c minus gamma. So, and this has volatility minus gamma sigma c by Ito's formula, and the risk premium is minus the volatility of marginal utility. So I take this with the minus sign. Basically, I get this equation, and this is the risk premium for CRRA. I think all of that I can erase. This I'm going to keep because I think it's useful to have this equation with a different numerator, except that this is the risk premium. This money example, I'm not sure if I need it, but I want to keep it, but I don't think I can afford to keep it. Okay. This I can probably erase, but I'll erase it later. All right. So it's always good to start with some example in mind. So we can think about this model, but with agents having CRRA utility. So they're experts in their household, but instead of them being risk neutral, they have CRRA utility with risk aversion coefficient gamma. Okay. And what I want to start with is I want to start by introducing their value functions. So I start with a notation for value functions. So they have, so let me write down the value function of experts as V times k to the power of 1 minus gamma divided by 1 minus gamma. Okay. So this denotes the proper definition of this. This is the, so if there was one expert, one representative expert, whose wealth share is eta, then this would be the utility of one expert with wealth share eta. Representative expert. Okay. So this is, and then if you want to basically find the value functions of experts with different wealth levels, then basically you have to scale it by. Okay. So this is the value function of experts, and this is the value function of this is the same for households. Okay. So I'm just introducing these definitions. And the idea why this is going to be useful is that we will be able to solve for the value functions by backward induction using some backward equations. And then we can use the value functions to get the risk premia, which we'll need for, where do we need the risk premia? We need the risk premia inside this equation. They come from the value functions. We need the risk premia inside this equation when we determine basically capital structure of firms and the allocation of assets. So we'll need risk premia here. And we need the value functions because from value functions we can determine the consumption rates of all agents. And we need consumption rates here for the market clearing condition. And also we need the consumption rates here for the equations of the law of motion of wealth. Okay, so it's useful. And, I might have missed somewhere else where where it can be used, but let me. Let me. I think it's enough. So. Okay. So one of the questions you may ask me is that, why I choose this notation for the value functions. So one of the things here is that, of course, the value function has to reflect the scale invariance of the model. So that's why basically I have to scale by k to the power 1 minus gamma. So that makes sense, right? But then one of the questions you may ask me, which is a very fair question, is, I could also write the function as, for example, omega times nt 1 minus gamma divided by 1 minus gamma. I could write it like this. Okay. And you may ask me, well, why I wrote it like this and I didn't write it like that. Okay. So, I mean, both are kind of like valid ways, right? But I choose that. And the reason why is that there's actually a very good reason, is because if you write it this way, then in the price of capital there is a kink in these models at the point of fire sales. And because of that, if you look at the total wealth as a function of the state variable for a fixed level of capital, the total wealth, of course, is going to have a kink. So in the end, there is going to be a kink but the value function has to be smooth. Okay. So this kink in n has to correspond to a kink in omega, right? So basically that could be a pain in the neck to deal with computationally. So basically that way you avoid the kink. So you could also write it so this way, it's just because of the kink, that's a better way. That's the way that works much better. I'm just saying, having taken the wrong turn at one point before. So another thing is, you could say that, well, why don't you write it, as something like this: Vt eta t1 minus gamma kt1 minus gamma over 1 minus gamma. Okay. So I mean, this is where you say, well, this is like the wealth to the power 1. So you could write it like this, where it's going to be a different constant, and I think this is going to work quite well. So you could do it this way also, right? But in order to put it in here, sort of like it makes sense that it should be there. So maybe let me call it instead of V, not to confuse colors. And I'm writing it in blue, which is less visible on the purpose because black is going to be more important. All right. So but let me break it down into two parts. One of the parts will be how to solve for the value functions. So you have to solve for them backwards. That's the part number one, and that part is going to have a numerical element. But the second part is going to be, suppose we were able to solve them, then how do we use them? Yeah?
That's the question from this. So are we somehow assuming that the experts derive utility from holding or owning the capital and there's no consumption problem for them? Or
I'm definitely not assuming that. Yeah, I'm definitely not assuming that. So this value function. So what is the value function? The value function is.
this is the value. Okay.
The definition of this is basically. Here's the definition of this. So the definition of this is, let's denote the aggregate consumption of all experts by Ct plus S. Okay, so all of the experts together, they will consume Ct plus S. And I take this to the power 1 minus gamma, and so this is the utility function of a representative expert. I discount back to time t, integrate from 0 to infinity ds, so I'm integrating s, and I'm taking the expectation of this at time t. Okay, and this expectation is that value. The value function is the value of this expectation. Okay, so over here, I wrote a value function in terms of wealth, and that's also a useful way of doing it. So let me transform it into the value function of wealth. Okay, so if we have this, which captures this expectation, right? Then it's useful to have an expression for the value function of an expert as a function of wealth. And in order to do it, we basically know that eta equals n over qk, okay, This is the wealth of expert over Q times K. So therefore K equals N over eta Q, right? That's one. So therefore, the value function is Bt K 1 minus gamma over 1 minus gamma equals B over eta Q to the power 1 minus gamma times N to the power 1 minus gamma over 1 minus gamma. So this is the value function expressed as a function of wealth, and this is for the total wealth of experts. But I can put if I want a smaller expert, I can put a different wealth. Okay. So the first order condition for the optimal rate of consumption is that the marginal utility of consumption has to equal to the marginal value of wealth. So that means that $1 put into tomorrow's wealth has to have the same value as the $1 put into today's consumption, otherwise the consumption choice is not optimal. So basically, C to the power minus gamma has to equal the derivative of this with respect to N equals V to power V over eta Q 1 minus gamma times N minus gamma. So basically I just differentiate this with respect to N. And I can also write it as because this ratio N, because N over eta times Q is equal to K, right? So I can write it in terms of K. So I have if this is equal to V over eta times Q times K minus gamma. Okay. And from this, I can get what? I can get C over K is an important ratio. So C over K equals, I guess, eta times Q over V 1 over gamma from that equation. And I can also get C over N. So from here, C over N is equal to eta times Q 1 over gamma minus 1 divided by V to the power 1 over gamma. And then something else that I can also get is that minus gamma sigma C, which is the volatility of this part, which is something that I need to know to figure out what the risk premia are, right? This is equal to the volatility of the right-hand side, so sigma V, it's a ratio, minus sigma eta minus sigma Q, and then minus gamma, the volatility of K. So the volatility of K is just sigma. So I have sigma, right? And if I want the risk premium, so the risk premium of experts is basically minus that. So it's going to be minus sigma V plus sigma eta plus sigma Q plus gamma sigma. Okay, so this is the risk premium that I got from the value function. This is the ratio of consumption to capital that they got from the value function. This is the ratio of consumption to wealth that they got from the value function. And this is going to be useful because it enters the law of motion here. This is going to be useful, the ratio of C over K, because it's going to affect the this part, the market clearing condition for consumption. Okay, so let me write down the market clearing condition for consumption. So the market clearing condition for consumption is that C over K plus C underlined over K. So this is the ratio of the consumption of experts and households to the total capital equals the ratio of output. This is the demand for consumption, and this equals the supply of consumption. So the ratio of total supply to capital is equal to the total output, which is A times psi plus A underline 1 minus psi minus iota. So this is the rate of investment. The rate of investment, of course, is a function of Q because it's determined by this condition. And the full market clearing condition is so C over K is eta times Q over B to the power 1 over gamma. And C underlined over K is 1 minus eta times Q over B underlined to the power 1 over gamma. So I'm assuming here the gammas are the same. But if you want them to be different, you can make them different. So this is market clearing for output. So this is the market clearing condition for output. This is one equation. We have here between these two market clearing. That's one of the conditions in our economy. And then we have asset allocation equation. That's another condition. Is basically this condition in our economy, which describes which is the first order condition for the allocation of capital. And then there is a third static equation, which has to do with endogenous risk. So this risk generation equation. Okay, basically this is the equation that determines sigma q. Let me describe this equation. So, so with endogenous risk, this equation gives the volatility of eta. So sigma eta equals psi minus eta divided by eta sigma plus sigma q. And of course, q is a function of eta. So using eta's formula, we have that sigma q is equal to q prime of eta divided by q of eta times eta times sigma eta. So this is the absolute volatility of eta, like not the geometric Brownian motion form, times times q, and this is the relative, so I have to divide by multiply by q prime and divide by q. And so I multiply both sides by eta, and I get that eta sigma eta is equal to psi minus eta times that. And if I want to get sigma q, then I multiply by q prime over q, and this is equal to q prime over q times that. Okay, and so and I can use this equation to solve for sigma plus. I can solve for sigma q, but let me solve for sigma plus sigma q. So sigma plus sigma q equals 1 divided by 1 minus q prime over q psi minus eta sigma plus sigma q. Just that. Right? Yeah, these two are equivalent, right?
Yes.
Yeah? Okay. So at this point, you really have to check my algebra, right? All right. So let me interpret this equation a little bit. This is the risk generation equation. Okay. This equation basically captures amplification, and specifically. So if the capital that experts hold is psi equals eta equals their wealth share, then basically the capital is allocated proportionately to experts and households, and in that case there's no leverage, and so the risk of capital is just going to be equal to the fundamental risk. Okay, but the risk is bigger than the fundamental risk when there's leverage. So when this is positive, and when Q prime is positive, then the price of capital basically responds to shock. Then this is going to generate amplification. So basically, this denominator reflex amplification, and that's why this is we can think about this as the risk generation equation. So that's that equation. So we have this equation, we have that equation. Let me rewrite this equation a little bit using using the explicit formula for the risk premium. So this is the risk premium of experts. The risk premium of households equals minus sigma B underline. And then I need the volatility of households' wealth share, which remember that the volatility of experts and households' wealth shares, their weighted average has to be equal to 0, and therefore this is the volatility of households' wealth share. And so the second term for the household's risk premium is I have to basically subtract that. And then sigma q is a common term, and gamma sigma is a common term. And the difference between these equals I have 1 minus eta over 1 minus eta sigma eta. So I'm looking at the difference, right? So so I'm going to have a difference of those two. So I'm going to have minus sigma v plus sigma v underlined. And then I have sigma eta plus, and then I have minus. So with minus minus is going to give me a plus. Plus eta over 1 minus eta sigma eta. Okay, so I have those four terms. So together they're going to give me minus sigma v plus sigma v underlined, and then plus sigma eta over 1 minus eta. Okay, so this is the difference between the risk premium. And by the way, from here, because this is eta sigma eta, I can get that sigma eta sigma eta equals to this times psi minus eta, psi minus eta sigma divided by 1 minus q prime over q, psi minus eta. Let me derive another formula for this. This is going to be is equal to minus v prime over v plus v underline prime over v underline plus 1 over eta 1 minus eta eta sigma eta, and yet another way of writing it is to plug in the eta sigma eta in there, okay? And after plugging in, then I can write this first order condition like this. underlined divided by Q equals, and then you have this part, which is minus B prime over B plus B over underline prime over B underline plus 1 over eta 1 minus eta times psi minus eta sigma plus sigma q squared. Okay. So I did it kind of in the wrong order, but it turned out kind of nicely because the three equations that I need are all lined up. But I just realized that they do not need everything that they derive. Okay, so let's take a step back. Okay, so it's not a huge step back, but a small step back. And see what we have. So if we have these, so what I want to claim is that if we have these functions, so we have value functions which are functions of the whole state space. So we assume that somehow we have a backward procedure to determine them at a given moment in time. Then what I want to claim is that we can use these three equations, and they're actually going to be equations, these three, okay, to get the allocation of assets and risk at any point of the state space. Okay. So this is what I'm going to claim. So suppose that we have the value function. So if we have so here's what we can do. So if we have b of eta and b underlined of eta whole functions. Okay. Then I claim that you can use these three equations, 1, 2, and 3, in order to get function q of eta and the entire state space, function psi of eta and the entire state space, and sigma super eta and the entire state space. Yeah, those three things. Okay. And then if we have those, then you also have the risk exposure of experts, and we have the consumption rates, which we have from this equation, and so then we can plug them into that equation to get the law of motion of the expert's wealth share. So basically, then we can get d eta over eta. So basically we already got the volatility, so we can get the drift from this equation. Okay. And we also have the risk linear, because if we have sigma eta, then we can basically just get it directly using this formula. Okay, so how can we get them is what we basically need to do is we need to determine the size of the region where fire sales happen, and we want to determine the function Q in that region, and then we want to determine function Q also in the region without the fire sales. So we can actually use these three equations to solve for function Q of eta through a first order differential equation. So that means we can have an initial condition. So we have some initial condition at 0, because at 0 we know that psi is equal to 0, and then we can solve this equation as an equation for a single unknown Q, and basically we have Q of 0 initial condition from 1. So Q of 0 from equation 1, and then we get eta and Q of eta. We get those from from solving the differential equation up until now, and then we have them. And our goal is basically to find Q prime of eta. And how can we find Q prime of eta? Is that if we have eta and Q of eta, then we can put them into a computer, and we can use these equations to solve for various parts. So let's see what we can solve. So we can use equation 1 if we have Q and we have V, because we know function V underlined. We can use equation 1 to solve for psi. So we can use equation 1 to solve for psi. Okay, and then well, can we use equation 2? Well, we cannot quite use equation 2, because in equation 2 we know psi, but we do not know sigma q, and we do not know q prime. Okay, but can we use equation 3? So in equation 3 we know psi, we know all of those derivatives, we know q. We just need to solve for sigma q. So we use equation 3 to solve for I guess sigma plus sigma q. Okay, for sigma q. And then after that, we can use equation 2 to solve for q prime. In that way, we can basically solve for the allocations through the first order differential equation. So in other words, taking a step back, if we somehow know value functions at the given moment in time, then we can use static equations to figure out how much endogenous risk is generated at each point, and we can use the static equations to figure out the distribution of risk, to figure out the distribution of capital, and as a result, from this equation, we can get the whole law of motion of eta.
Which equation we use to solve for Q eta?
For Q. So we have an initial condition from this equation, because we know that at eta equal to 0, psi equals to 0. And so this is a single equation for Q. Okay. And after that, this sequence gives us q prime at each point if we know q. Okay. So if we know q prime, then we can find q at next eta plus a small amount, and then we have the next q, and then the next q we solve it, and then we get the new q prime, and we can keep going. Yeah.
Yeah, I think just directly solve 2 for the function q. It's a first order linear differential equation, so there's a solution formula.
To solve 2 for function q.
Yeah.
Yeah. So if we know sigma q, which is a function in the whole state space, then we can solve this equation directly, right?
Yeah, that's sort of.
But in general, we do not know what is sigma q, so we have to solve for sigma q as well. And so basically, we have this intermediate step to solve for sigma q.
But
Yeah.
But you could, I mean, you don't need to approximate. I mean, the last step, I guess you need to approximate to get the next point.
Yeah, right, exactly. So it's a numerical scheme. Yeah. Okay, so anyways, so there's this part which I think is interesting, but the next part that I want to talk about is like even I think the next part is even more useful because it's more general. And that is the question of how to solve for these value functions. Okay. So this is the full value function, and Vt it's a coefficient. Okay, and at each moment in time, after a particular past history of shocks, Vt is going to have a particular value. This value is going to be a function of eta. Right? So V is a function of eta. And the value function equation in general takes this form. So so this equation is basically just well, this equation is just a simple application of a ethos formula. Yeah, this is not the value function equation. This is just ethos formula. So so suppose that we are solving for this function v backward in time. Okay, and suppose that v is the function of time and also the function of state. Then ethos formula tells us that this is the drift of v. Okay, and it equals to the first derivative of v times the drift of eta plus the second derivative of v times the volatility of eta squared divided by 2 plus the time derivative of v. So this is just Ito's formula. So Ito's formula gives this equation. So so what do we know in this equation? So in this equation we know the drift of eta, and we know the volatility of eta because we have a way of solving for those. Okay, and I'm also going to say right now, but I'm not. But I didn't show you yet, is that there is a way to solve for the drift of v. So how to solve for the drift of v, I'll tell you in a moment. Okay. So if you know this part, and if you know this part, and if you know this part, then basically what this is the backward equation for the value function. Okay. And this is an equation that can be solved numerically. How to solve it? So I'll tell you in a moment. Solving numerically. I'll show you in a moment. But in order to solve this equation, we need to know what is the drift of v. So where the drift of v comes from. So let me derive the drift of v. So what I'm going to do is I'm going to use this definition of the value function. Okay, and from this definition of the value function, suppose that I take the expectation at time t of the integral from 0 to infinity e minus rho s c 1 minus gamma s over 1 minus gamma ds. I take this expectation. Then this expectation equals so this is a martingale. Okay. Why this is a martingale? Because by the law of iterated expectation, because this is the total utility that the expert gets from time 0 until time infinity discounted to time 0, and we take the expectation of the same process at different dates and times. So that's why this is a martingale. And this is a martingale, and so I can decompose it into two parts. But this expectation, because I can take the part that's known at time t outside expectation. So at time t, it's already known. This is already known. But what is not known is basically the expectation at time t of the future pair. And what I have remaining is basically e minus rho t times the future value function, which is v t k 1 minus gamma over 1 minus gamma. Okay? And I know that this is a martingale. So because this is a martingale, the drift of this process has to be 0. So the drift equals e to the power minus rho t times. So to get the drift, I basically have to differentiate it with respect to t. And to differentiate this integral with respect to t is just differentiation with respect to this t. So by the fundamental theorem of calculus, I get ct 1 minus gamma divided by 1 minus gamma. Then I differentiate this product with respect to t. And to differentiate this product, I have minus rho times dt k 1 minus gamma over 1 minus gamma. Then I have plus, I differentiate v, so I have mu v times k 1 minus gamma over 1 minus gamma. And the rest, this is just, and then the rest, I guess you can get from Ito's formula. So let me see if I can quickly derive it. Sigma is v sigma. I think this is the whole formula. Okay. So, you can check my algebra at home. But the point that I want to make is that from this equation you can get mu v. Okay, you can basically get mu v from this equation. And in order to get it, you will have to divide by k to the power 1 minus gamma, and then you will have to use this formula in there to get c divided by k. So basically this formula, you use it once in the market clearing condition, and another time to get this mu v. Okay, but basically from this you can get mu v. Okay, and the intuition about mu v is that, well, this is this has to be a martingale if this really represents the value function, and therefore the fact that this really represents the value function gives you the appropriate drift, basically to satisfy the promise-keeping condition of these experts. So basically, this procedure gives you mu v, which is a whole vector of the state space. So that's the function of the state space. Any questions? Okay. Now, let me talk about how to solve this equation.
Sorry.
Yeah.
To get mu v, we need v, right?
We need v, yeah.
But we don't have v. Is there an iterative scheme there?
Ye-
An outer loop?
Yeah, so what I suggest to do to solve for v is we're going to solve this backward equation for v, which means that we'll specify some terminal condition in the distant future, and then we solve for it backwards, right? So at each time, as we solve backwards, we have v at that time because we arrived at the value of v at that time through the backward procedure. And then this equation, we come to it having v at a particular time, and this equation gives us vt, and this is basically going to be a derivative with respect to t. Okay. So basically, you can see already that you can basically solve this equation as a system of vector equations for v backwards in time. So it's a system of so in what system? This is a system of ordinary differential equations, and in what sense is this a system of ordinary differential equations? So it's an ordinary differential equation for vector v. So v is a vector on. You basically have 0, delta, 2 delta, and so on and so forth. 1. This is the values of eta discrete. Okay, and here you have, let's say, you have 1,000 points. Okay, so basically, it's a vector with, or you have 1,001. Okay. You have 1,001. You have 1,001 grid points. Each one of them is a length of 1 over 1,000. And as given that whole vector, and also given the vector v underlined, so you actually have I guess. 2 vectors to solve for simultaneously, for v and for v underlined. So at each time point, you have to go through this sequence of steps to determine at a given moment in time, allocation and risk, and the drift and volatility of eta. And then you also determine mu v and mu v underlined. You plug it into this equation to determine basically the time derivative, and this equation basically gives you the whole vector of time derivatives of this whole vector, and then you can solve it backwards. So how to solve it is one way to solve it is you can use built-in MATLAB function, MATLAB OD solver, to solve this vector OD. Okay. So what does it mean? It means that you have to program this ODE function, which means you have to program a function that takes in a vector of v's and a vector of v underlined on the whole state space eta, and then it takes those 2 vectors and it performs this sequence of steps to find ultimately the drift and volatility of eta, because you're going to need those, and to also find the drift of v. So to find the drift of v, you will need the volatility of v, which you already found through that process. You will need the ratio of consumption to capital, which you already found over there, and I guess you will need the growth rate of capital, which is phi of iota minus delta. So you found through this process. So basically, you get this, and then this function will take the v, will go through that sequence of steps, and the output of the function will be the vector of derivatives of v with respect to time. Okay, and then what you need to do is that this function that you wrote, you feed the built-in MATLAB ODE solver a function handle, a net function, and just solve it. And MATLAB ODE solver knows how to handle ODEs, and it just solves backwards basically is discretized with respect to you discretize it with respect to the state variable, and the built-in solver figures out what's the best way to discretize it with respect to time and solve it backwards in time, and you get the answer. Okay. So when you do this, here's something that's useful to know. So MATLAB has various ODE solvers. Okay. And I think one called ODE45 is an explicit ODE solver. And I think there's more than one explicit, and I think there's more than one implicit. So if you use one of the MATLAB solvers to solve this equation, which MATLAB ODE solver you should use? You should use an implicit one. Okay. And the reason why is that the explicit one will also work, but will work much, much slower. So basically, the next point I want to make is that use implicit. So to figure out if it's explicit or implicit, what do you do? Type help. Use implicit ODE solver. Okay. Oh, there is one more thing that I should. No, I think I should. Yeah, I should tell you. I should tell you one more important thing. How to write this function to get Vt out of this whole equation. Or you could write your own solver. I think that's even better to write your own solver because you leave fewer things in the black box. So why to use implicit ODE solver? So so it has to do with stability. That so here you have a spatial step for this differential equation, which is delta. And given the spatial step, in order for the numerical scheme to be stable, and what does it mean stable? It means that if it's unstable, it's gonna blow up like crazy. So in order for it to be stable, you need the time step dt to be of the order of delta squared for explicit scheme. Okay. So that means that if you have 1,000 spatial steps, then MATLAB will need to take 1,000,000 time steps. And if you want 10,000, then MATLAB will need 100 million time steps. So basically, the time step has to basically be quadratic in the space step. And why that's the case? I mean, you can open a book and PDEs, but this is for explicit scheme. But for implicit, it's only order of delta. Okay. Okay. So this is something that's important to know. So something else which is also important to know is if you use a MATLAB solver, right? And if you want to get this this time derivative, you will need to compute these derivatives yourself. Okay. So basically, you will need to compute those derivatives from the grid point, and how to compute them. It's not so it's not rocket science. So for example, v double prime is equal to v of let's say of n. So there are n grid points. V double prime of n equals v of n plus 1 minus 2 v of n plus v of n minus 1 divided by delta squared, and that's your approximation. Okay, so it's not rocket science. You can basically discretize it that way. Okay. But so that's for the second derivative. But the first derivative, you can compute it. Well, you can compute it in this way: v of n plus 1 minus v of n divided by delta. So you can go forward, or you can compute it as go both ways, or you could compute it going backwards over v of n minus v of n minus 1 divided by delta. You can compute it this way. And a naive guess would be that you can do it this way, or you can do it that way, and which way you do it doesn't matter. Okay. But it turns out that it matters really crucially whether you get convergence or not, and whether your scheme will converge, which one you use. And which one should you use? Should you use this one, or should you use that one? And the answer is, well, you have to test the sign of the drift every time. And you have to use this one if the drift is positive, and you have to use this one if the drift is negative. Okay. So there are all of these things that you have to worry about. Okay. So so I've been working with this, and one of the things that they have realized at one point is that an equation of this form comes up all the time. Okay, and so basically it's an equation, and so I decided that for me personally, because this equation comes up all the time, it would be useful to just write the function to basically solve any equation of this form, so that when it comes up the next time, I don't have to program it again, but I can just use the function that I wrote 3 years ago. Okay, and so then what I decided to do is to write a function called I called it something like payoff policy grows, and it takes in eta, which is the state space. So I'm sort of doing from memory. It takes so R, R is basically, this is like mu B. It takes mu, it takes S, and I think it takes dt. Maybe it's slightly more general. Maybe it takes one more thing. And basically, any equation of this form, R times V equals mu times V prime plus S squared times V double prime divided by 2 plus VT. It basically, so it basically takes those coefficients and solves for V one step backwards. Okay. Of length t. Okay. And this function, so inside this function, obviously has to basically evaluate the derivative of. Oh, so of course you also need v. Okay. So basically, yeah, you also need v. So basically, you have v, and then you solve for it backwards. One step dt, and then this is the function, and this is the function that I use, and if you, and it's useful. Okay, so so it's useful to have to name this equation. What should we name it? We could call it the value function equation, but it's really for these growth problems, right? Because basically this coefficient, it takes into account, well, the discount rate, the growth, and actually the payoff flow, because the payoff flow is a part of it. This is the payoff flow, right? So I could take some time to show you the code, but I think that it's probably better if sort of like if you explore it yourselves, right? I think that there's some code already online on the Princeton Initiative website, but what I'm going to do is I'm going to update it a little bit because I know how to make it a little bit better. And something else which I also do for the Princeton Initiative is that for those of you who want to get into it a little bit deeper, what I do is that each year I write a problem set, okay, and I have a problem set from the previous year, from the previous year. So what I'm going to try to do this year is that each time when I still have some energy left, I try to write a new problem set. So I'm going to probably write it maybe by Wednesday next week, and then I will email you, and then it will be posted. And for this problem set, I encourage all of you to take a look at it, and if you want to do it, I highly encourage you to do it. So from the date that you receive it, you will have basically 2 weeks. And I know that you're busy, so you do not always have time. So I hope that in those 2 weeks, at some point you have a little bit of free time, and you can spend it, trying to solve the problem. And that the problem set is going to have a numerical portion, but the first portion is basically going to be an analytical portion, reusing some of these calculations. And whatever solutions you have, you can send them to me, okay? And to create a little bit of incentive for sending in the solution, besides the fact that I know that you did it. So one part of incentive is I know you did it. So I remember who did it in the previous years. But another part of incentive is that I also will write my own solutions. But I will only send them to people who send me their solutions. So my own solutions, they will not be posted freely on the Princeton Initiative webpage. You only get those if you send me your solutions. And then we will take a look at your solutions, and we'll also send you my solutions. Yes. Okay. So I should say one more thing, because so this is one question you may ask me is okay, so there's a function to solve this equation, okay, so that's useful, and solve it backwards from the terminal condition, okay, that makes sense. Well, you may ask me the question, well, how do you set the terminal condition? So how do you set the value function at the last state? And basically, the answer is you can set it in any way you want, as long as it's somewhat reasonable. Okay. So if you set it, to 0, right, at the final date, then I actually have not tried doing it, but I think that this is not reasonable because then things are going to blow up as you go towards the final date, because if your terminal date value function is 0, then as the date approaches, you're basically going to eat into everything very, very fast, and then obviously everything is going to blow up, right? So unless you shoot yourself for the blowing up, set some conditions. So set some value function. So for example, one value function is to set motivated by something like this. Set v equals to the constant times eta 1 minus gamma. So something like that, for example, could be reasonable. It doesn't matter what is the constant, as long as it's not 0. Well, actually, whether it's positive or negative, you have to make sure to get the sign right. So I think positive. It's got to be positive. Unless unless I have my brain is not functioning, it's got to be positive. So you said that to something like that, it's going to work. And the idea is that you run this economy for 1 million years, and what you're solving for, as you solve for it backwards, is you're solving for an actual function in the actual economy in a hypothetical situation that at the final date, 1 million years from now, you have some regime change, and that regime change is going to give you that specific value function. Okay, so maybe some technology is going to change, and then you take that value function is given 1 million years from now. Okay, but right now, what happens 1 million years from now? I mean, it's not going to matter a whole lot, and so things are going to converge. Okay, and so basically you get as you solve for it backwards long enough, you basically get this stationary equilibrium. Okay. So does the terminal condition not matter at all? So that's one question you could ask me, and I'm not going to say that it doesn't matter completely. Okay, so here's one curious fact. Okay, so suppose that you solve a model with money, and then you have another equation which is also backward equation, like the value function equation, except it's the money equation. And then you solve for it backwards. And the question is, well, what terminal condition do you set for the value of money at the final date? And you could set the value of money to 0 at the final date, or you could set the value of money to epsilon at the final date, or you can choose, some value of money. So, for example, you think that 20% of total wealth at the final date is money, so you set it to 0.2. And then you solve for it backwards. So then, depending on the level of risk, okay, you could have an economy where there's no equilibrium with money. And if there's no equilibrium with money, then whatever you set the terminal condition to, as you solve for it backwards, the value of money is going to converge to 0. Okay, if there's no equilibrium with money. So the final date, it's something, but as you solve for it backwards, the value of money is going to converge to 0. But if you have an economy in which there is an equilibrium with money, and there's also an equilibrium without money, then here's what you're going to get. So if you set the terminal condition to exactly 0, and you solve for it backwards, money is worthless a million years from now. By backward induction, it's also going to be worthless, at any earlier time. So basically, you're basically going to get 0 in that case. But if you put epsilon at the final date, and if you solve for it backwards, it turns out that no matter how small the epsilon is, you're going to converge to the full value of money as you go back basically early enough. And basically, it's kind of interesting because like a small perturbation that gives money an epsilon value in the long run is actually going to make money basically worse. The full stationary value in as you solve for it backwards. And this fact is related to another statement that I've learned from Chris Sims. And basically he says that, well, if you have like a monetary economy and there are 2 equilibria, there are many equilibria in between maybe, but if you make money backed by epsilon of taxes, then that immediately selects the equilibrium in which money has value. Okay, and basically this fact is a little bit related to that.